So you now know how to calculate Kc and Kp and how to read a graph of concentration over against time and rate against time. But what can K tell you? Simply by looking at the numerical value of it. If K is an expression of the concentration of products over reactants at equilibrium, a large K will tell us that at equilibrium, the concentration of products is much greater than the concentration of reactants. If K is small, it tells us that at equilibrium, the concentration of products is far lower than the concentration of reactants. From K, we can tell which way the position of the equilibrium lies, whether it lies to the left of the equation or the right of the equation. But what if the system is not in equilibrium yet? Can we use K to tell us which way the reaction will proceed? Yes, it can, but we must first know whether there is an excess of products or reactants first. To do that, we create a term called Q, or the reaction quotient, which is simply substituting the reactant and product concentrations or partial pressures at any point during the reaction into the equilibrium constant expression. I do not need to know at which point in time Q was taken, but from just the numerical value of Q, I can tell which way the reaction will proceed to attain equilibrium. Since Q is also concentration of products over reactants, just not at equilibrium, if Q is smaller than K, this means that there is currently now less products than there should be in equilibrium. Therefore, the reaction will proceed in the forward direction, to the right, to create more products to attain equilibrium. Similarly, if Q is larger than K, this means that there is currently too much products and too little reactants, and the reaction will proceed in the backward direction, to the left, to reduce the amount of products to attain equilibrium again. Now what if Q is equals to K? Well, congratulations, you have reached equilibrium and there is no incentive for you to shift anywhere else.